Guys, we are going to indicate intervals on which this function is increasing or decreasing. This is going to give us some practice with the product rule and also give us a little bit of rehearsal with what it means for a function to be increasing or decreasing when it comes to appealing to its derivative. So, step numero uno, as it often is here, is going to be to take a derivative. So, hang on, let me get rid of the cursor. That thing always has a nasty habit of showing up when I don't want it. There we go. First of all, I'm going to take the derivative of this function. Because it is the product rule, I need to do f prime g plus g prime f. Or since I'm already using f, I'll just say derivative of the first times the second plus derivative of the second times the first. So here I've got x to the power of 1/2. And here I've got e to the x. I'm writing it as x to the 1/2 because it will be easier to think of it that way so I can apply the power rule to that. F prime of x is going to be the derivative of the first. That'll be 1/2 times x to the negative 1/2, and then times e to the x. And then I'm going to do plus the derivative of the second times the first. Now the derivative of e to the x is e to the x. So this will be square root of x times e to the x, where that e to the x that I wrote there in the second part, that is a derivative. So, okay, it can be a little bit simpler to understand these things if I factor out whatever I can factor out. And also I'm going to rearrange this. So this will be plus 1 over 2 square root of x. In case that's not clear, this right here is 1/2 times 1 over x to the 1/2. And that will be 1 over 2 times square root of x. So in case you're wondering where that came from, that's how I got that. Now I want to examine this to see where is this positive or negative. Because where it's positive, the function will be increasing, and where it's negative, the function will be decreasing. But this is a weird question because actually this function, this derivative function, is made of a bunch of parts. There's this, which is always positive. This, which is always positive. Always, well, I wrote it one way one time. I wrote it the same way the second time. That's always positive for suitable inputs. And then this is always positive as well. So we have all positives here, and they're linked only by multiplication and a plus sign. So what does this mean? It means that as long as I put in a value that's in the domain of this derivative, it will yield a positive value. I don't need to get into the details of solving an equation where this is equal to 0 and then I look on either side, because in this specific case, it's nice and clean. It's plus times plus plus plus. Well, there's no way that that could give me a negative answer. So I know that this is always going to be, come on, I know this is always going to be greater than 0 on its entire domain. Where is that domain? The domain of the function is from 0 to infinity, inclusive of 0, because I can evaluate the square root of 0. But the derivative has this on the bottom. The square root of x is on the bottom. So this means that I cannot put in 0 for x in the derivative. This has to mean something for the graph as well. Remember that the graph of square root of x has a vertical tangent right there, and that means that its derivative doesn't exist. Well, what this probably means for this more complicated function is that it has a vertical tangent there as well. So we're going to say that this derivative is greater than 0, and it will be greater than 0 for x in the interval from 0 to infinity, not inclusive. So this derivative is positive on its entire domain, and so this function is increasing on the interval from 0 to infinity, and is never decreasing. Okay, let's do another one. Same sort of question, indicate intervals on which the function is increasing or decreasing. But this now is going to be using the quotient rule instead. So f of t is that. I want to find f prime of t. Well, here, I'm going to see if you can handle using different letters. U and V, meaning top and bottom. This is going to be, yeah, I've got room to write it there. It's going to be u prime v minus v prime u over v squared. Derivative of the top times the bottom minus derivative of the bottom times the top, and then on the bottom you divide by v squared. So f prime of t is going to be equal to derivative of the top. This is 2, because after all, the top is 2t. So derivative of the top times the bottom, that's 4 plus t squared, minus derivative of the bottom, that's 2t, and then times the top, that's 2t. Again, it's a coincidence. On the bottom, you divide by 4 plus t squared, and then you squared that. So when you do quotient rule, usually what happens is you have this big messy thing that gets handed to you on the top, and then you gotta like multiply out, combine like terms, and do a bunch of simplification. This is no exception. So we're gonna have 8 plus 2t squared. That's from doing this multiplication. And then it will be minus 4t squared all over 4 plus t squared squared. There's one more step of simplification, and it's based on these two being like terms. So this is going to end up being 8 minus 2t squared all over 4 plus t squared squared. This is a more complicated function than the one we dealt with before, because this actually will be positive and negative at different times. To see where those things are going to happen, it's sufficient to look at just one part of this. Think about the top versus the bottom. So the bottom of this is squared, right? There it is. It's a square. Not talking about this. I'm talking about this one right here. So, yep. So this will be positive or negative, not when the bottom turns between positive and negative, because it's always positive, but it will be positive and negative according to the top. Whenever the top is positive, this will be positive. Whenever the bottom is positive, this will be positive. I'm sorry, I misspoke. Whenever the top is positive, this will be positive. Whenever the top is negative, this will be negative. So it's sufficient to consider the top alone since the bottom is always positive. The bottom doesn't even give us any domain restrictions either, because usually when there's something on the bottom of a fraction, there's like the danger that you're going to end up dividing by 0. But that's not going to happen here, because 4 plus t squared can't be 0, because t squared isn't going to be a negative number as long as t is real. So the bottom just can be completely ignored in terms of getting the intervals where the function is increasing or decreasing. Let's go and do it. So we're going to have 8 minus t squared equals 0. Remember, when you want to solve for something being positive or negative, first of all, you look for where it's equal to 0. And then you look for that as the boundary point. You say on either side of that, is it going to be positive or is it going to be negative? But it all starts with saying when is it equal to 0. This is a nice, easy equation. We're going to end up getting 2t squared equals 8. T squared equals 4. And oh, look, isn't that just so nice when it turns out all nice and neat like that? So t is equal to positive and negative 2. Now, we could do a thing where we like make a number line and say, where is the derivative positive? Where is the derivative negative? But I like to do things graphically whenever I can. So I'm going to say a graph of 8 minus 2t squared would look a little bit like this. It's a parabola, right? I'm not saying the original function was a parabola. I'm saying that 8 minus 2t squared is a parabola. And it's an inverted parabola because the squared term, the quadratic term, has a minus sign. So those 2 points right there, put them in red, beep, beep, those right there, those are the points where the derivative is 0. Because it's an inverted parabola, we know that on this side it's negative, and on this side it's positive, and on this side it's positive, and this side it's negative. So this gives us very easily the fact that the derivative will be positive on this interval, because that's where the top of the derivative is a positive number. And it will be negative on these intervals, because those are the intervals where the top of the derivative, and thus the whole thing, is negative. Okay, so we're one step away from being able to state this. It is increasing on the interval where the derivative is a positive number, and that is from -2 to +2. It is decreasing everywhere else, because everywhere else the derivative is a negative number, and that would be from -infinity up to -2. Union, you could just use the word or if you like. You can even use the word and, as long as you don't mean the technical definition of and, because you can't be in both one and the other because they don't touch, but that's a different story. So it's increasing on this entire interval from -2 to +2 because that's where the derivative, shoop, is positive according to its top. And it is decreasing on these two intervals because that is where the derivative is negative, shoop, according again to its top. So we have answered the question. Cool, huh?